to Net Points. Very often UGC Net aspirants gladly omit a particular portion from their syllabi, and that is the automata theory, mainly because it doesn't belong to the arts and science stream. Now today we are going to see some basic concepts from that particular topic, and the first thing that we are going to see is languages and grammars. Now, why languages are important? Languages are needed for communication, for conveying some message. So in the context of automata theory, we are talking about automatons or machines. Machines which are capable of accepting input, processing it, or storing it, or producing the desired output. That is the model of the latest or the modern digital computer. But there were earliest or abstract model of the digital computer. They were the Turing machines, and which were later termed to be the automatons. So the earliest or the abstract model was the Turing machine, and it had its own input unit, output unit, input tape, output unit, storage, processing unit, and everything similar to the modern digital day computer. Now, as far as languages are concerned, each language is constructed, or it has a grammar construct. Every language has its grammar. So what are the different languages and what are the different grammars on which these languages are based? The languages that are accepted by the different automatons. So that we are going to see today. So Turing machine was invented by Alan Turing, an earlier computer scientist. Now here, first we'll talk about grammars. And talking about grammars, we should know what is meant by Chomsky hierarchy of grammars. In this hierarchy of grammar, we have four hierarchies: type 0, type 1, type 2, and type 3. The type 0 grammars are also known as unrestricted grammars, or the grammars or the languages that are based on these grammars are unrestricted language, or they have another name for this, and that is recursively enumerable languages. Unrestricted languages are also known as recursively enumerable languages. Now, these languages are accepted or identified by Turing machines. So, Turing machine is capable of accepting or identifying these languages. Next, we have the type 1 grammar, which is a context-sensitive grammar. And the context-sensitive grammar can be fed into a machine or automaton known as linear bounded automaton, and this is linear bounded automaton is yet another type of a Turing machine. It is a type of a Turing machine which is less powerful than the Turing machine but more powerful than finite automaton and push down automaton. We'll come to the differences of these different types of automaton after this explanation. Now we have the type 2 grammar, which is the context-free grammar. Context-free grammars are identified by deterministic push-down automaton, or recognizable by deterministic push-down automaton. Then we have the type 3 grammar, which is a regular grammar. Regular grammar can be accepted by finite automaton. Now this is the Chomsky hierarchy. As I told you, unrestricted grammar are known as recursively enumerable grammars, and all these grammars fall into a class called the recursive grammar. Recursive. Okay, so context sensitive, context free, and regular belong to the recursive language, whereas unrestricted grammar belong to the recursively enumerable language. Right, so this is the basic understanding of the Chomsky hierarchy. Now we'll go into the details of these automatons. So first we'll talk about the Turing machine. Turing machine was invented by Alan Turing as I told you, there are certain important points to be noted. If the Turing machine accepts a language, then it will halt and say, and it will respond with a yes. If it rejects a language or rejects a string from a language which it is not capable of identifying, then it will halt and say a no. In both these cases, the Turing machine will halt and will respond with a yes or a no. There are 8 other languages which the Turing machine are not capable of understanding. In that case, the Turing machine will go into a loop. It will not halt. And this is known as the halting problem of the Turing machine. And the problems which fall under these categories respectively are termed as desirable and undesirable. And there are also semi-desirable languages. So the desirable languages are those on which accepting strings from which the Turing machine halts, whereas undesirable languages are those where the Turing machine accepts strings. It cannot accept strings from that particular languages or from those problems. So if the Turing machine halts and responds with a yes or a no, then the languages are said to be desirable languages. If it doesn't halt, but it simply continues to loop, then it is known as undesirable problem. Next, we are going to talk about linear bounded automata. So as far as Turing machine is concerned, we have 2 important things to note. One is the halting and the looping problem. Now we have what is known as the linear bounded automata. These are machines, these are Turing machines only. These are Turing machines. Linear bounded automaton is a Turing machine, but it doesn't use all the space in the tape, just like the Turing machine. The Turing machine is capable of using the entire tape space, whereas the linear bounded automaton does not use the entire tape space. That is why it is more powerful. Okay, so the tape space is limited to the input size. Say for example, if the input that you are feeding to the linear bounded automaton is ABC, then the tape space is limited to ABC alone. And how it is limited? What are the delimiters here? Is some kind of a initial and a final marker. So on seeing this, we can understand that the tape space is limited to only this. Actually, if you go in detail, it is not actually this space. The Turing machine or the linear bounded automaton actually assigns k times the size of the input, which means that we have 3 characters. Then k is a constant. K is a constant. K times this. If you have k is equal to 3, then 3 into 3 is 9. So it allocates 9 cells on the tape. Of course, along with the delimiters. So here, what is the basic understanding? The basic understanding is the linear bounded automaton, the space is limited according to the input size. It doesn't use the entire space in the tape, and it will not go beyond the left hand marker or after the right hand marker. So either way it won't travel. Right? So as far as linear bounded automaton is concerned, it is powerful, much powerful than finite automaton and with push down automaton, but somewhat less powerful than the Turing machine. Okay, so next we'll come to the next automaton, which is the finite automaton. So what is a finite automaton? Finite automaton is the simplest automaton that is used to recognize patterns. It has a set of states and the machine moves or makes it transit from one state to another depending on some rules. So as far as finite state automaton is concerned, we are talking about states here. A finite set of states and a transition table which allows a transition between these different states. Say for example, and this finite automaton is represented by a 5 tuple. What is a 5 tuple? So finite automaton are basically represented by 5 tuples. One is q, next is small q, then set of sigma, then finals f, then delta or tau. Now here capital Q stands for set of internal states. Set of internal states. Small q stands for the start state. And here this symbol sigma stands for input. Input symbols, the set of inputs. F is the final state. And here this is the transition or the transition rule as we say here. It is given by a transition table. Now this is a 5 tuple which is used to denote a finite automaton. Now here, what is a state here? So this capital Q collectively the set of states in which the finite automaton can be at any point of time. Now this is an example of a finite automaton. This is the schematic diagram for any example, a particular automaton, finite automaton. If you see here capital Q is equal to Q naught, Q1, Q3. I can say capital Q is equal to Q naught, Q1, Q3. Small q is the initial state. See, it is the starting state. So when you feed something into this state, so you can just feed it only to this state. Okay, so this is the state which directly accepts the input. And so here Q naught is the initial state. Then next, what is the sigma here? The set of inputs, input characters or alphabets or symbols that can be fed into this. Okay, so here there are two inputs A comma B. So I can say this sigma is equal to A comma B. Then I have F, which is the final state here, which is the final state here in this diagram. The final state here is Q3, and how do I distinguish it from the rest of the states? By means of concentric rings. If I put two rings, okay, around a state, then it means that is the final state. Then this delta is the set of transition rules or transition table. Now let me say the transition rules according from this diagram. What is the transition rules? From Q naught, if I give the input A, then the machine will go to the state Q1. From Q1, yes, from Q naught, if I give the input A, the machine will go to Q1. From Q1, if suppose the machine is in state Q1, if I give the input as C, it will remain in Q1 itself. So this is used for looping, or this is something like a closure or clean closure. Usually clean closures are represented by star, and we have yet another operation plus. I will tell you the difference between these two. So on C it will remain in Q1 itself. On B it will go to Q3. Q1 on B goes to Q3, which is the final state. So this is a set of production rules here, okay, or transition rules here, and this is a transition table. So if you look at the entire finite automaton schemas, it can be represented by 5 tuples. And what is the string that is accepted by this particular finite automaton? I can say first the string that is formed here could be A and a B. They are, by default you should have an A and a B, because without A and B we cannot move from one state to another. But the C is optional here. The machine can make a move using the C, or it is left completely optional, because in order to reach the final state I need these two for sure, right? So what are the characters that are needed for sure in order to reach the final state? That is, by default it will be present in all the strings that is accepted by this automaton. So what are the other strings accepted? It could be A, C, B, or it could be A, C, C, B, or A followed by any number of C's, B. So this is what is meant. This is the language acceptable by this finite automaton. So here the star represents 0 or more occurrences of the character C. So this is the language. A, C star, B is a language that is accepted by this particular automaton, and these are the strings. Okay, so this is infinite number of strings, but the pattern is, this is the pattern, and therefore this is a language identified by this automaton. Okay, now there are two different types of automaton, a finite automaton. We have a deterministic finite automaton and non-deterministic finite automaton. So what is a deterministic finite automaton? Deterministic finite automaton, non-deterministic finite automaton. In deterministic automaton, we can know the future behavior of the automaton based on the present status or the present condition in which the automaton is currently. It could be the state of the input or the state of the processor, anything. So based on the current status, we can determine the future behavior of the automaton. So those automatons are known as deterministic finite automaton. Whereas in the case of non-deterministic automaton, the automaton can be viewed or imagined as a set of many finite automatons, or a set of many machines working at the same time, just like we have in a distributed computing system. So here it is not possible to predict the future behavior of the automaton. There are various differences. There are a number of differences between a deterministic finite automaton and a non-deterministic finite automaton. And the main thing is that here possible to predict the future behavior, whereas here it is not possible. Second thing is, in deterministic finite automaton, given a single input, there can be only a single state transition. There can be only single state transition. Whereas on a single input, there can be multi-state transition. Which means if I give an A, I can go to Q1 or Q3 or any other state for that matter in case of NFE. Whereas if I give for single input, a single transition is only possible. Whereas in both the cases, it is possible that two characters can be to the same input, same state. For example, if I give A, if I give either a A or a B, it can lead to Q2 or Q3 or whatever. So for a single state transition, there can be more than one alphabet which can lead to that particular state in both the cases. Whereas at a time, only a single state is allowed in terms of deterministic finite automaton. Whereas here, you can traverse to multiple states. So in a deterministic automaton, The string is said to be accepted in a deterministic automaton only when the string at the end of the string, the machine reaches the final state. If you are giving ABC at the end of C, if the machine is in final state, that is here Q3, then we can say that that particular automaton has accepted the string. If not, we'll say it has rejected the string. Okay, that is the acceptance or rejection state of a deterministic finite automaton. Whereas in the case of non-deterministic finite automaton, here there are multiple branches, right? Because we have several state transitions and several inputs leading to the same state. It is like multiple meshes. There are several branches. So even if the string does not reach, or the machine does not reach a final state at the at the end of one string in one branch, there are other branches also. So if the machine does not reach the end of the string at the final state, it will leave that branch and it will traverse to the next branch in order to find whether the condition is satisfied. So if in any one of the branches, if this condition is satisfied, then there we are saying that the NFA accepts the string. Can you follow? Because here there are multiple branches, so any one branch needs to satisfy this condition, right? Multiple branches. Any one branch is enough to find out whether the string is being accepted or being rejected. And there is something called the empty string transition. So here, deterministic automaton does not allow empty string transition, whereas NPTA allows an empty string transition. What is an empty string transition? That is without any input itself, just on being giving an empty string, the machine will transit from one state to another. That is what is known as empty string transitions. So this is these are two different types of automaton. I told you the difference between these automatons and the points that are to be noted between in these automatons respectively. Okay, we'll go to the next automaton, which is the push down automaton.